Okay, so as in the last video, we have discussed about Pauli's exclusion principle. Before that, we discussed about Venn diagram. In Venn diagram, we discussed about the superset. Then we discussed about the subsets as well. Initially, we discussed about four quantum numbers: the principal quantum number, azimuthal quantum number, magnetic quantum number, and in the end, spin quantum number. Then we discussed this principal quantum number is the superset, which means all the quantum numbers lies in it. Alright, then azimuthal quantum number is the subset of principal quantum number, and then magnetic quantum number is the subset of azimuthal quantum number, which means principal quantum number is the superset, and these both are the subset of the principal quantum number. Then I wrote this, which means n is greater than L. N is principal quantum number, L is azimuthal quantum number, and M is magnetic quantum number. So n is greater than L, which means principal quantum number is greater than azimuthal quantum number, and azimuthal quantum number is greater than magnetic quantum number. Afterwards, we discussed about Pauli's exclusion principle, in which he said that no any two electrons were going to possess these four same set of four quantum numbers, which means if I have two electrons, they can possess three same quantum number, which means they can have same principal quantum number, they can have same azimuthal quantum number, even they can have same magnetic quantum number, but their spinning would always be different. If one electron would be spinning clockwise, then another electron would be moving anti-clockwise. That's why only because of their spin quantum number their quantum number changes. So that's why Pauli said that no any two electrons would gonna possess four same set of quantum numbers, which means their spin quantum number would always be different. Their three quantum numbers can be seen. Alright, so in today's video we are going to discuss the electronic configuration, which is the very last topic or very last subtopic of this entire chapter, atomic structure. Alright, what does electronic configuration mean? So electronic configuration describe where electrons are located around the nucleus of an atom. For example, for suppose if I have a nucleus here, for suppose I have an atom, and in that atom I have a nucleus, and I know that electron has probability wave. Alright, so now where this electron can be present, this is what we call the electronic configuration. Electronic configuration is basically the location of the electrons. This is nothing but it is the location of the electrons. Alright, so electronic configuration describe where electrons are located around the nucleus of an atom. As you can see here, the definition which is written on the screen. So where the electrons are located around the nucleus of an atom. Now, before going towards the rules of electronic configuration, we're going to discuss each and everything in very detail. What is a Farr principle, what is Hund's rule, we're going to discuss each and everything in very detail. But before that, we should discuss about electronic configuration of numerous elements. Alright, we have a lot of elements in periodic table, but we're gonna only take few elements among those, and we're gonna discuss electronic configuration of those. Then we will be discussing the rules of electronic configuration of Farr principle, Hund's rule, and we have already discussed about the Pauli's exclusion principle. Alright, so initially we have one S. Alright, in we know in you know what, in first shell we have only S, so we're gonna write 1s. This I should make with white actually, so 1s. Alright, and in S we have 2 electrons, so let's write here 2 electrons. Alright, then so as you can see in the second shell we have S as well as P. So here I'm gonna write 2s since that is second shell, and there we have 2s and P as well, so 2p. And we know that in S we have 2 electrons, so in S we have 2 electrons, and in P, as you can see here, we have 1 2 3 4 5 6 electrons. So in P we have 6 electrons. Now going towards third one. So third shell, all right. In third shell we have SPD. So here 3S, 3P, and 3D. Alright, in S we already know we have 2 electrons. In P we have 6 electrons. Alright, now let's see how many electrons do we have in D. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 electrons in D. 10 electrons in D. Alright, now moving towards the fourth one. Alright, as you can see fourth here. So here we have S, B, D, F. We're gonna write here 4 S, 4 P, 4 D, and of course, wait, let me move this a bit so that I can have space here. Alright, now it is bit fine. Alright, so 4D, and here I have 4, you know what, F as well, right? And in S we have already known 2 electrons, 6 electrons in P, 10 electrons in D. Let's see how many electrons do we have in F. So let's count this. Wait. Here we gotta go. So in F we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we have 14 electrons in F. Alright. So how many electrons do we have in S? We have 2 electrons in S subshell. We have 6 electrons in P subshell. We have 10 electrons in D subshell. And we have 14 electrons. In F subshell. Alright, as you can see here, it's already written here. 2 S holds 2 electrons, P holds 6 electrons, D holds 10 electrons, and they have not written about F. However, F holds 14 electrons. Alright, so now how are we gonna make this? We gonna make like this. Here arrow, it would gonna be here arrow, here arrow, here arrow, here arrow. Alright, so we're gonna make electronic configuration here, which means initially electrons, wait, let me write this here. Initially electron would be going in 1s2, then 2s2, then 2p6, then 3s2, 3s2, alright, then 3p6, then 4s2, then 3d10, then 4p6, and so on. Alright, so initially electron would be going in 1s2, then 2s2, then 2p6, then 3s2, then 3p6, then 4s2, and then 3d10, then 4p6. Alright, now let's see the electronic configuration of Na, which is already you can see on the screen. Alright, in the next video we're gonna write electronic configuration of various elements. However, for this we're just gonna look into it since it is already available on our screen. Alright, so sodium, we have here on our screen the electronic configuration of sodium. We know that how many sodium has electrons. It has 11 electrons. Alright, because electrons are always equal to the atomic number, and atomic number of sodium is 11. So 11 electrons sodium will gonna possess as well. Alright, which means sodium has 11 electrons. Sodium has Sodium has 11 electrons. Alright, so how they is gonna be filled? Alright, we know that initially electrons will be going in 1s2. So 1s2, which means 2 electrons are now filled by the s subshell. Alright, now we need to fill 2s2. Alright, so 2s2. So 2 electrons are again filled by s subshell in the second shell. Alright, now 2 to 4. 11 minus 4, we have again 7 electrons left. Alright, now we need to occupy 2p6. So 2p6. Now let's count how many electrons have been occupied by the subshells of the shells. So 2 plus 2, 4. 4 plus 6, 10. 10 electrons have been occupied by the subshells of the shells. Now only one electron is left. And now we need to know that this electron will be occupied by which subshell. Alright, now we have 3s2 turn. However, wait, where it has gone? Okay, now it is turn of 3s2. But if I am counting this, 2 plus 2, 4. 4 plus 6 is 10. 10 plus 2 is 12. However, we know that sodium atomic number is 11, which means there should be only one electron in this subshell. So this 3s2 will gonna possess only 3s1. Alright, so electronic configuration of sodium atom would be 1s2, 2s2, 2p6, 3s1. If you can count this all, if you can count 2 plus 2, 4. 4 plus 6, 10. 10 plus 1, 11, which is the atomic number of sodium. Alright, so in the next video we're gonna look more into the elements. We're gonna take every element till 30 and we're gonna write its, the electronic configuration. We're gonna read the rules as well of Power principle and Hertz's rule, and we have already discussed about the Pauli's exclusion principle. So this was all for today.